Hello, today we are going to see how memory of a supercomputing system is organized. The performance of a supercomputing system depends upon how well the memory serves data and code to the CPU. Hence, understanding the nuances of memory subsystem is very important. This is the agenda for today's lecture. We will begin with the basics of memory technologies. Then we will see how hierarchically memory is organized and the role of cache in it. Then we will see the different types of memory architectures, namely symmetric multiprocessing, non-uniform memory access and cluster. So, let us get going with the basics of memory technologies. So, here we have shown 4 types of memories which are commonly used: the static memory, the dynamic memory, the flash memory and the hard disk. Each one of them uses a different basic storage element and they have other characteristics like volatility and the speed of access, as has been indicated in these 2 rows. Now, the reason why each one of them is used for a specific purpose is shown in bold. Like static RAM is used as a cache memory because it gives the fastest access. Dynamic RAM is used as the main memory because it has got best density and capacity. Flash memory is used as an accelerator between the main memory and the hard disk because it is faster than hard disk and it is used as solid state drive. Finally, when we want the highest capacity, we used hard disk as a secondary storage, but we have to also appreciate that it is the slowest of the all because it uses rotating magnetic medium. To understand further, let us first see how CPU accesses memory. So, here you have the CPU and this is the memory. Between them you have the address bus which provides the address to the memory, and the memory either reads or writes the data on the data bus. Whether the CPU is performing a read operation or a write operation is indicated by a signal. So, let us see how read works. So, read is initiated when a load instruction is executed by the CPU. It begins with decoding of the instruction. Once the CPU knows that this is a memory read cycle, along with the load instruction it will get the address from where the data is to be read. CPU takes this address and puts it on the address bus, and as a result the memory, which also sees the read signal, starts reading the data from the specified address, and once it reads it from the specified address, it puts it on the data bus. Once it puts it on the data bus, the CPU accepts it and the read cycle is completed. Now, let us see what happens for a write. Write is initiated by a store instruction that the CPU receives. Along with the store instruction, the address and the data where the data is to be written is specified. As a result, the CPU puts the address on the address bus, puts the data on the data bus, and the memory accepts that data and stores it at the location which is specified by the address. So, these are the 2 basic cycles that the CPU performs on memory. Now, let us see what are the requirements from the memory subsystem. As far as programmers are concerned, they would want unlimited amount of fast memory, so that there is no restriction on the data they want to use, the code they want to use, and they want the memory to respond in the fastest possible manner. But the reality is that fast memory is costly. So, though you can theoretically put all the memory as SRAM, which is the fastest, but the power that it will consume and the money that will cost makes it unviable. However, if you analyze the way the accesses to the memory take place, as I described in the previous slide, you will find that it shows a principle of locality. There are two types of localities. One is temporal, that is when the CPU begins access on a particular location, there is a good chance that the same location will be accessed subsequently in time. Similarly, spatial locality indicates that if location X is accessed by CPU at some point in time, it is likely to be followed by accessing X plus 1, X plus 2, etc. So, that is the spatial locality. Now, taking this in consideration, the principle of locality, we design a type of memory subsystem in such a way that the system creates an illusion, which means it is not a reality, that you have fast memory and it is unlimited in size. How it is done? We will understand it when we understand the cache subsystem. Now, let us look at some of the things that have happened historically. When microprocessors were introduced, the standard memory parts were faster than the contemporary microprocessor, meaning that if the microprocessors needed the data, let us say in 150 nanoseconds, the memory could provide it within 120 nanoseconds. As can be seen here, that the memory and the speeds of the memory and that of processor are matching with each other. But as this graph shows, the processor's speeds have typically increased 52% annually, whereas memories have become faster, but they have not been able to keep pace with the speed at which the processors expect it to serve the data. As a result, what has happened is a gap in the performance has occurred, because of which the CPU would keep waiting for data to come from the memory, because they are working faster, whereas the speeds of the memory are not same as what the CPU expects. So, the next question for us to answer is, now that we have identified that there is a performance gap, how do you bridge this gap? One of the things that hardware designers try is interleaving the memory. That means, instead of having one unified bank of memory which has a common address and data, we have more than one bank, let us say two banks. So, address 0 will be in bank 1, address 1 will be in bank 2, address 2 will be in bank 1, address 3 will be in bank 2. Like this, in odd and even banks, the alternate addresses are mapped. As a result, when the CPU is reading from contiguous locations, it accesses bank 1, then bank 2, bank 1 and then bank 2. What is the result? The result is that while one bank may be slower, the access to the second bank can start before the access to first bank finishes. As a result, the delays can be elevated to a certain extent. Another thing that is tried is increasing the memory bandwidth. While the speed cannot be increased, one can always increase the bandwidth by taking wider memory path. What it means is that in one cycle, which is continues to remain slow, you are getting more data. So, the amount of data that you get within a time is more, because the speed has not reduced, but the paths have become wider. For example, Pentium is a 32-bit CPU. However, the data path from the CPU to memory is 64-bit, which means that in one cycle the CPU is able to fetch 2 words from the memory. Thus, the memory bandwidth is increased. Other than this, the most commonly used way for improving the memory performance is using cache memory system. I had already indicated to you that SRAMs, which are the fastest, are used to implement cache memory, and as a result this memory helps in giving the data to the CPU at the fastest possible speed. But also remember that this memory consumes more power, and this memory is costly. Per bit cost for a SRAM is highest, hence we try to restrict its size. So, let us understand how the cache fits in the hierarchical memory. So, what is this memory hierarchy? Let us try to understand. So, this again works on the principle of locality that I had indicated earlier. There is a temporal locality and spatial locality, that is what it takes advantage of. So, now we have seen that we have memories like SRAM, DRAM, hard disk, flash memories, which are having different access speeds, they are having different densities and they are having different cost. So, you construct a memory subsystem which is consisting of multiple levels. One level will have SRAM, other level will have DRAMs, and finally you will have the hard disk and the SSDs will sit in between them. The way it is organized is fast memory, which is obviously going to be slowest, as I mentioned earlier, is put closest to the processor, and as the levels go away they become slower and bigger. So, what is the goal of this hierarchical system is that you provide the maximum memory that you need, which is the cheapest, and of course it is going to be slowest, whereas since you have put the fastest memory closer to the CPU will be able to access the memory at the speed that is offered by the fastest, that is the SRAM. And because it is small, it is not going to hold all the data. All the data is going to be held in the maximum memory, which is the cheapest and which is away from the CPU, and in between you have multiple levels. So, the data, when it is not found in a level closer to the CPU, it is copied from the adjacent level, and this goes on. And when it is closest to the CPU is able to run fastest, and this is called as a hit. If it not found, then it is called as a miss. And the system tries to maximize the hit rate, because if the CPU is able to find the data in the memory which is closest to it, which is fastest, it is going to perform best, and that is why more the number of hits, better is the performance of the system. Pictorially it can be shown like this, that this is the ALU where the data is finally going to go. Typically it comes from level 0 cache, which is the registers. So, you would be aware that every CPU has got certain number of registers. So, that is where the data will be served fastest, but they are very limited in number like 8, 16 or 32. As a result, beyond the registers there is level 1 cache. The data which is in level 1 cache will come at the fastest speed, which will be fed to the register, and most of the time the register operands are fed to the ALU. A slightly slower but bigger in size is level 2 and level 3 caches, and then comes the main memory, which is implemented as DRAM. All these 4 caches, that is level 0 to level 3, they are implemented as SRAM. Then you have a local hard disk where the virtual memory is implemented in the swap area, and if that space is not enough for you, you can finally go to the remote storage which is on the server. So, as you can see in this diagram, as you go closer to the ALU, the size of the memory becomes smaller, but the access time becomes faster and the per byte cost also increases. Reverse is true as you go away. So, now let us see how cache is implemented. The word cache originates in the dictionary as a safe place for hiding or storing things. However, in case of hierarchical memory, the cache memory sits in between the main memory and the CPU. So, its purpose is to act as a sort of a fast buffer between the CPU and the main memory. As far as the cache is concerned, it is, since it is smaller in size, it will contain a copy of portions. This is important, that you cannot have the size of cache as same as main memory, it has to be smaller. Hence, only some portions in the main memory which are frequently used, they are maintained in cache. So, the typical algorithm would be that the CPU makes a request for a word, like it is trying to read a word which is 32 bit. This address is put on the address bus. This address is now checked in the cache whether this address is present in the cache. If it is present in the cache, then the data is immediately written and it will be faster. However, this may not be always true because cache is having only certain portions of the main memory. In case there is no hit, that means the data is not found in the cache, then the cache controller will further send the address to the main memory. Main memory will respond with a block of data. A block is a collection of words, like CPU is trying to read 132-bit word, whereas in this case 4 or 8 32-bit words would be transferred from the main memory to the cache. The reason for taking a block of data is the principle of locality. We had said that due to spatial locality, it is likely that the address, let us say x, that has been found to be a miss, which is now brought in the cache, along with it x plus 1, x plus 2, x plus 3 and x plus 4. These addresses are also brought into the cache. Thus, with a hope that subsequently these addresses would be accessed by the CPU. So, this is the basic principle on which the cache works, that it is a small amount of fast memory sitting between the main memory and the CPU. Now, let us see how the principle of locality is implemented by the cache. So, we have said that principle of locality is observed and this is what the cache takes advantage of. So, let us see how the temporal and spatial locality are handled by the cache memory. It works on the fact that if a memory location is accessed by the processor, then the same location will be accessed by the CPU next time as well. Now, example like a loop has a index, like you write a statement like for I equal to 0 to I less than 10, I plus plus in C. So, every time the loop is run through, the value of I is incremented, which means suppose the loop is executed 100 times, the value of I is going to be accessed, it is going to be increased. Hence, it makes sense to keep this value of I in cache. This is what temporal locality guides us. Spatial locality means that if a memory location is referenced by the processor, it is very likely that the subsequent addresses are going to be referenced in the near future. Let us say you are processing arrays in a loop, then array elements are accessed one after another. So, if you can get a block of these elements from the array at one time, in the next instances the subsequent addresses will be served. So, these are the two principles on which cache works. Now, what are the contents of a cache subsystem? There are three parts in it. First one is the directory store. The cache should know where did the data originate from in the main memory, because the ownership of any data is with the main memory. Cache is just a temporary storage. Hence, when the CPU generates an address, the cache has to first check whether the data is available in the cache. How it will do that? It will do that based on the directory store, and this is called as a tag. So, tag indicates where did the data originate from in the main memory. Then the important section, data section, this will hold the actual data because this is what will be served. Along with it, it has some status bit, that is whether the data is valid, because initially the cache is empty. Only when the data is brought for the first time, the valid bit is indicated as 1. Similarly, there is an issue about non-coherency. Non-coherency means data in the cache and the data in the main memory is not the same. This will happen in a multiprocessor systems or multi-host systems, in which case there is a bit called as a dirty bit. This bit indicates that the data in the cache is not same as in the main memory. And always remember that the main memory is the owner of the data, and all attempt is made to keep the data in the main memory correct. or fresh. This picture shows us how the data is organized in the cache. So, as I have already indicated, cache is sitting in between the main memory and the processor. This consists of 3 parts, out of which status bits are not shown here. This is the tag and this is the data. Now, this tag indicates that this location is fetched from location 100, this is from 101, 102 and so on. This location is fetched from 580, this will be 581, 582, 583 and so on. So, this is called as a cache line or a block which has contiguous addresses in the main memory, and always it is organized as a collection of lines, and associated with every line is a tag. So, you have the data portion, the tag portion and the status portion, which will be again available for every line. Now, to manage all this, we need the cache controller. What does the cache controller do? It will look for the addresses that are generated by the CPU. It will check the address whether that address matches with any of the tag. If not, then it will copy the data from main memory to cache memory automatically. Now, this operation is transparent to the CPU and the software, though the cache controller driver would be aware of it, but while the software is running and if the cache is enabled, the software will find that the data is coming very fast. So, its job, the job of the cache controller is to intercept the operations, read and write operations on the main memory which the CPU is doing, check whether the tag matches, then serve the data from the cache or pass on them the access to the memory controller. And there is also to facilitate this operation, there happens to be a relationship between the main memory and the cache, how the cache is organized, and this is called as mapping. So, what I have mentioned in the previous slide is depicted in a flowchart manner here. So, the read algorithm for the cache is as follows: CPU generates the address, the cache controller looks at the processor address, looks for the tags whether any of the tag matches. If it is found, then the data is served from the cache, and this is fast, and this we will call it as a hit. If it is not found in the cache, this is called as a miss. And remember, a line or a block is read from the main memory, that is stored along with the tag in the cache, and the data that comes is sent to the processor. Of course, while sending it to processor, the cache is updated and the data can now be served from there. Now, there are multiple lines in the cache, as we saw. Where will this data go? In which line will the data go? That question will always come in our mind, and that is answered by the mapping scheme. So, there are 3 types of mapping schemes. One is called as a direct map, the other one is called as a n-ways set associative, where n can be 2, 4 or 8 or so on, or there is an extreme of this which is called as fully set associative. Unfortunately, we do not have time to get into details of this, but each one of these schemes has its advantages and disadvantages. Now, it would be important to know how the performance of this cache system is measured. So, hit rate is the term that we use to indicate how well the cache system is. Hit rate is a ratio of how many times the data was served from the cache vis-a-vis the total number of memory requests. So, hit is the primary way of hit ratio is the primary way of understanding cache efficiency. One can also quantify it, that how many cycles are taken when there is a hit and how many cycles are needed when there is a miss. I had mentioned about cache coherency. It arises when the data in the cache is different from the data in the main memory, which means one of the data is stale, that is either the cache has updated data or the main memory has a updated data. This problem does not come in a uniprocessor systems where there is only one CPU. However, when you have multiprocessor systems, that is more than one processor accessing the main memory, then this cache coherency problem may pop up. One of the ways to avoid this problem is what is called as write through policy. That means the main memory is always updated when the cache is updated by the CPU, and to know whether other processors have been updating the main memory, the cache controller of CPU 1 looks for the memory bus, checks the accesses that are happening on the memory bus and sees whether any writes have taken place to any of those locations whose copy is maintained by its cache. So, that was our discussion about cache, which briefly would give you an idea about why it is needed, how it works and how it improves the performance. Now, coming to the main memory, let us recall the MIMD kind of architecture which we studied in the previous lecture. In this case, we have multiple instruction streams which are working on multiple data streams in the multiple execution units. So, how is memory implemented for such processors? There are two ways, one is called as a shared memory, other is called as a distributed memory. So, this tells us how the two types of memories are organized. So, in shared memory it is also called as tightly coupled. The distributed memory is also called as loosely coupled. In case of tightly coupled, you can have SMP, that is symmetric multiprocessing, or you can have non-uniform memory access. Clusters are an example of loosely coupled memory architecture. Now, coming to the SMP architecture, its definition says that a computer system having two or more processor with similar CPUs will qualify to be an SMP. The characteristic of these processors as compared with the memory system is that all the processors that are there, they will share the entire memory as well as IO facilities. So, there will be an interconnection by means of a bus or a switching matrix which connects the memory subsystem to all the processor. The basic characteristic is that the access time for all the processor is same, whether processor 1 accesses location memory location 10 or processor 2 accesses memory location 10, the access times are going to be same, and all the processors have got access to all portions of the memory. The good thing about it is that the operating system finds such kind of architecture to easy to deal with, because there are no constraints, every processor has got access to every portion of the memory at the same speed, that is symmetric multiprocessing. This diagram tells us how it works. So, here there is processor 1 which has its local cache, like this you have processor n which has its local cache. This is the shared bus that connects all the processor to the unified memory. Similarly, on the bus IO subsystem is also existing. Now, here you can see that all the processors have got equal access to the memory and they access it at the same speed. This is how SMP works. Now, coming to the non-uniform memory access. To understand non-uniform memory access, first we need to see what is uniform memory access, which is what I described in case of SMP in the previous slide. To recall it, all processors have got access to all parts of memory, access time is same and access time for all processor is also same. So, that makes it unified memory architecture. Now, let us see how non-uniform memory access works. The first part is same, all processors have got access to all parts of main memory. However, the fact lies in that some portions of the memory may be accessed in a fast way and some portions of the memory may be accessed in a slow way, which is based on which part of the memory a particular processor is accessing, and this is true for all processors. To tell it in a different way, let us say processor 1, there are two, it has got a set of memory addresses, let us say it is the total address range is Z, out of which one portion is X, another portion is Y. Now X portion of the memory will be accessible at a fast pace, Y section of the memory will be accessible at a slower pace. X plus Y will constitute Z. Now this is true for each processor, that it will have some region which is fast and some region which is slow. That is why the word non-uniform memory access time. This is how a non-uniform memory access architecture looks like. You have this memory which is closer to this processor, this memory which is closer to this processor, and together all memories form a unified range. So if processor 1 is accessing a closed memory, it will be faster, but if it has to access a data which is in this memory, it is going to be slower. So now why can't we make all systems with SMP? Why NUMA is needed? That is because there is a limit, practical limit how big a SMB can be, and typically the limit is 64, though this is not a theoretical limit. The reason why NUMA scores over SMP is because it gives a flat addressing model, which means a single OS can run in the computer. However, it overcomes the limitation that SMP puts in, and it can go to literally thousands of physical processors or core, and one of the examples that is Silicon Graphics Incorporated had made this Altix ICE 8400 system, which had large number of cores running into tens of thousands. So this is an example of NUMA implementation where you have two nodes, node 1 and node 2, which are connected using an interconnection network. This has got its own private memory. So these CPU cores will have closer access, faster access to local memory. They will have a slower access to this memory, and vice versa is true for this set of CPU, which is closer to this but farther away from this. So for this a practical implementation of this is a server board with 4 CPUs, each having its own memory. Finally, we come to the cluster. By definition, you would have seen as we saw in the earlier lecture, that you have a switching fabric which connects n number of compute nodes, and this is a fast network with high bandwidth. What are the benefits why we go for cluster? First important thing is scalability. You can have literally thousands of machines, which in turn is a multiprocessor. It could be NUMA or an SMP. It gives you incremental scalability, meaning today you may have 100 nodes, tomorrow you can add 100 more nodes, the network switch will scale. Availability is an important thing. If one of the node fails, the software can manage to pitch in another node in its place and the cluster can work. The most important thing is its superior price performance, because each node is a sort of a off the shelf available node which has got much lower cost. So though you put in money in building the network, but the low cost of the node helps in reducing the overall price of the cluster. So this cluster is connected by an HPC network whose primary job is moving data from memory of one node to that of the other. Two attributes are very important for this network, that is very high bandwidth, that is amount of data transferred in a second, and it also depends, it is directly proportional to the link speed which connects the nodes to the switch. Then comes the latency. This includes the overall time taken from the first byte of the packet till the last byte of packet to reach the destination from the source. The latency comes into picture when you have small messages to send. The bandwidth comes into picture when you have large amount of data to be sent. Then finally, you can also add intelligence in the network. which is called as offloading. That means the network interface card can take up the job of transferring the data, checking its correctness and resending the data if needed. This relieves the CPU of this task. To end up, let us look at what we studied today. We mentioned that there has been a performance gap between the faster CPUs and the relatively slower memories. The answer to this is building hierarchical memory system, and an important element in this hierarchical memory is the cache memory, and it plays a significant role in providing the data at the fastest possible rate, and these caching systems work on the principle of locality. If you look at the main memory, it can be implemented in many ways. The tightly coupled ones are SMP, symmetric multiprocessing, and non-uniform memory access, whereas the most popular architecture today for supercomputers in the cluster, which implements a loosely coupled memory architecture. And the reason for clustering is so common is because of its scalability and cost effectiveness. I hope you got an idea about how the memory of supercomputing systems are designed so as to give a good performance as well as scalability, which is achieved through clustering, which is the most commonly used architecture today. Thank you.